Today, we're thrilled to welcome Rajeeb Hazra, CEO of Quantinuum, a leading force in quantum computing. In this episode, we'll explore where the industry is heading, the challenges it faces, and where Raj believes the crucial next steps in the field truly lie. We'll also delve into how quantum computing could help companies save billions, its potential for integration with AI, and much more. Get ready for an exciting discussion. Let's jump right in. Hi, everyone. Welcome to Research at Citi podcast. I'm Rowe, U.S. Regional Director of Research here at Citi, and I'm thrilled to have as our guest Dr. Rajeeb Hazra, who is the President and CEO of Quantinuum, which is a leading quantum computing firm here in the United States. Raj, thanks for being with us today.
Thanks, Raj. It's wonderful to be here. Thank you for having me.
Quantum computing is in many ways a complex subject. And it's also something I think that's getting a lot of media attention right now because of its absolute potential. And I've obviously personally gone down the rabbit hole on this. I'm fascinated by it, its connection to quantum dynamics. I'm not so sure that all of the participants and listeners on our podcast fully understand what quantum computing is. And I know that Feynman famously said, if you think you understand quantum dynamics, then you don't. So I'm going to ask a very tough thing of you, Raj, which is, can you explain to us, just for starters, what is quantum computing and its impact in a few minutes to get started so that people have an understanding of what quantum computing is, as opposed to what they've already known in terms of the classical computing world?
Yeah, thanks. That's a great question. And what I'd say is actually our knowledge of classical computing is a detriment here. And it's only a detriment here because classical computing in bits of zeros and ones and even Boolean algebra was all created by humans. It isn't how nature operates, right? We created a number system. So if someone saw 8 stones, how would you write that down and tell someone I saw 8 stones, right? Mm-hmm. So we had a numbering system, a logic system, a computational system, all built for how we thought we could compute. We could compute in zeros and ones. Mm-hmm. Well, while we were busy doing that as a society, from time immemorial, nature has been computing. And it computes not by creating big fabs and chips in it. It does it by natural elements and the natural phenomena, which is really what quantum mechanics is, which govern the behavior of those natural objects. These could be atoms, this could be ions, this could be photons. These are all things nature creates. So quantum computing is an entirely different paradigm in which the representation of information is not zeros and ones. It's a combination of a bunch of different kinds of states that the count could be in. And it's highly parallel because you can represent all of these states at once and compute on them all at once because they are all represented at the same time, right? So think of an object that you're using to keeping count with that it could only have 4 states or 6 states, right? So you can only represent to the power so many of those states. What if it could represent the whole gamut of potential states that something could take? And now you can compute with it with another of such an object that could do the same. So you get, in classical computing, the more bits you add, you get a linear increase in performance. In quantum computing, every quote-unquote qubit you add or state you add is an exponential increase in your ability to compute. I know this sounds no easier than, opening the first pages of quantum mechanics, but it is. The reason it's so hard to understand is because we've trained ourselves to understand the paradigm of zeros and ones and adding and subtracting zeros and ones on machines that we've built that can deal with representing a 0, representing a 1, and representing their arithmetic with them. Quantum computing is natural objects. They could be, again, atoms, ions, photons, even superconducting material that humans can create, or maybe even naturally found at some points in time, and using those as your abacus to actually do computing. The end result is it's much more energy efficient, and it's much more parallel, and therefore you get a much higher degree of performance. I'll bridge to the second question you asked is why is the hell everybody suddenly talking about quantum computing? We live in a world today where that human-made ones and zeros, the paradigm we chose to represent numerical information and compute on it, is running into severe walls. One is of energy. The more compute you want to do, we're burning up, gigawatts of power next to a data center, an AI data center. It's getting hard to have these massive infrastructures be reliable, right? The more things you have, it's Murphy's Law, but in a scientific sense, right? Something will go wrong. So reliable systems, affordable, energy efficient systems are the walls that classical computing is seeing. And quantum computing is now mature enough, both as a technology as well as its understanding that people say, hey, I can solve problems much more easily with far less energy or far less compute or in shorter amount of time. And most excitingly, more accurately than ever before. Mm-hmm. And I hope we get a chance to talk about one or two examples of where quantum computing is delivering each of these benefits.
Yeah, I do want to get to impact and some exact examples or applications of that. When we talk about the structure of these computers and the nature of what you're doing, in other words, using atoms essentially or ions as your qubits, there's an issue about control, about not only controlling these ions, but also making sure they're error free, as I understand it. Are those some of the particular challenges and hurdles in terms of having, I guess, what you'd call a coherent system?
That's right. So let's talk about if you're going to build a quantum computer to take advantage of this massive parallelism and what I would call resource efficiency, and you're using nature's tools, then you have to be as good as nature in managing them. That is, creating them, controlling them, making sure that other things don't disrupt and destroy their information while you're controlling them and doing computations on them. So if you bring it down to you need more and more qubits, or you need bigger and bigger machines, or you need more and more of these natural objects. That's called building things at scale. And with scale comes two challenges. Or to get scale, you have to, no pun intended, scale two challenges, right? One is, as you get more and more qubits, how do you keep them error-free? And there's lots of ways errors creep in. Some of these objects are like ice cubes. They naturally, even if you put them in a pristine environment, they will lose their information over time. It's called decoherence, right? So how do you improve coherence times of these objects? Second is, as you manipulate them, there's different sources of error. There's things like crosstalk, when these two objects can move like by each other, right? And there's when you're trying to manipulate the object, like trying to understand what is the information in the object, you could actually destroy the information or get errors in the reading. So there's different sources of error that you have to manage with innovations in the control systems, in the cryogenics and the environment, so that you can build bigger and bigger, but more and more reliable systems, so that you're not getting bigger, less reliable, right? And that is both a science challenge as well as an engineering challenge, because sometimes it's like the physics is understood, but you have to build extremely small miniaturized things like lasers and actually integrate them with other parts of the system. And that becomes an engineering challenge, right? Mm-hmm. So that's one. How do you scale without losing information or improving what's called the fidelity of the computer is a challenge, right? And in that, the industry has set a goal for what's called a fault-tolerant, universal, fully fault-tolerant quantum computer at scale. That's the race. And that's what we're proud to say we are leading in. And I can talk to you about why. The other is the challenge is software. We kind of sometimes get this hardware wonky hat on and keep thinking it's only about the hardware. It's about the software too, right? If you go back to this is how nature operates, well, nature doesn't run a college course on how to write algorithms for how nature is, right? So you have to start reimagining algorithms. I mean, I'm a signal processing guy by training, right? I learned the Fourier transform, well, I'll give my age away, but X years ago, right? And that's been the tool for how you analyze signals, right? Whether you're doing image processing, whether you're doing video compression, whether you're doing pattern recognition, that's what it, or spectral material discovery. It's all about Fourier transforms and understanding the spectral nature of those signals or that data, right? It's a fundamental tool. Well, if you're going to try and do that on a quantum computer, you got to come up with an entirely new algorithm that is consistent with the laws of how quantum mechanics and quantum mechanical behavior has to be governed, right? So there's hardware challenges, and you could then build a huge fault-tolerant, fully fault-tolerant universal quantum computer. But if there's no software that can take advantage, the algorithms that implement these primitives, the applications then that use multiple primitives, you're not going to get much. And you cannot just port existing software to quantum computers. No, this is not like, oh, there was first there was mainframes and mainframe software. You kind of ported to x86, and from x86, you kind of ported to ARM. But generally, the architecture was the same. It was more of a software port. It's like I'm trying to say the same thing to you, Robert, but
Right.
instead of saying it in German, I'm kind of saying it in Italian, right? So, but this
Yeah.
is not it. This is like some completely different language because the expression of information, the expression of computation is completely different. So there's a body of work that folks are doing, and we are doing because of our history with both hardware and software, we're doing in creating new algorithms. So both of these two have to come together. The hardware has to be more capable, more reliable, and the algorithms have to be more sophisticated and addressing larger and larger, kind of use cases, as we call it, for quantum computing to accelerate and become kind of really mainstream in the way we today take GPUs for granted, right? 10 years ago, 12 years ago, people were wondering, what do you do with these things other than graphics? How do you program these nasty devices, right? Which break all the laws of von Neumann computing we've learned so far. But lo and behold, today you can't think of life without GPU farms and
Right.
And the AI that runs on them.
Let's talk about Quantinuum a bit here too, and about the accomplishments that you've had in the development of these computers. You all have probably the highest fidelity of any computer. Maybe you can correct me if I'm wrong. And that also you have some of the longest coherence times. But also, I remember at the NVIDIA GTC when Jensen Huang was interviewing a lot of different heads of different quantum computers. There was this idea that the first milestone has to be a 100 qubit logical qubit default tolerant computer. What is the significance of 100 logical qubits? And talk a little bit about what Quantinuum is doing. And I know that you're what we would call a trapped ion modality, and maybe we can talk a little bit modalities after that.
Sure. You've asked a number of very interrelated questions, so I'll unpack them and I'll answer in a different order than you asked the question, but hopefully it makes sense to the listener.
Perfect.
Right. So we use, when I said natural objects for computing, we use ions, right? They're not like trapped ions, like you find them under a rock trapped or something, but they're ions, right? So we take atoms, which are plentiful in nature. The good thing is nature creates identical atoms, right? So we don't have to do quality control on our supplier. Nature just gives us, identical atoms. And then the process of creating an ion from an atom is well understood. You eject an electron out of it with energy. Why do we make it an ion? Because then you can use electrostatic forces to move and control these, right? Because they are charged devices. So you can use charges or electrostatics to effectively and to do that. So that's the modality we use, right? Mm-hmm. Our philosophy has from day one been to build the most performant quantum computer from the user's perspective. It is not about, I have 1,000 qubits, you have 500 qubits. It does not matter. It is what a customer would say, if I wanted to implement this algorithm, yours is the best one. And best in what respects? It is the highest performance. I can use the qubits and I get the right answer. I get the right answer with the minimum amount of execution effort, right? So time to solution. I usually get the right answer more often than wrong, right? Or more accurately. Then there's also your computer is also the easiest to write code on. That's both a feature of the hardware as well as the software tools we provide, right? So we look at it very much from a customer centric, not our numbers we can report. Like I've got 56 qubits or 100 qubits, I've got 20 qubits more than you, but what can you actually do? Can you run benchmarks? And in that, when we say we are the most powerful quantum computer, it's not because of one specific number like a qubit number or a fidelity number or a 2-qubit gate fidelity number. It's because we say you take the industry accepted benchmark of today called quantum volume and you run it on every quantum backend and see what the benchmark reports. And we are orders of magnitude, not 2x, 3x, better than number two. We're number one. We have been number one consistently for the last, from H1 to H2. And we see Helios not deviating from that. In that. And our philosophy is not lots and lots of fairly useless qubits. It's the maximum number of qubits we can give you where you can use all the qubits for meaningful computations. Mm-hmm. So we worked very hard in hardware and software to build qubits that have high coherence times, low crosstalk error, low state preparation and measurement error. So we minimize the errors. We build it in an architecture that makes it very much more amenable to be able to effectively run error detection and correction, because as much as we try to make them error-free, the hardware itself, there are going to be errors and quantum error correction is going to be needed. The question is, can your hardware be designed in such a way that makes error detection easier and more accurate and correction more effective? Because not all systems can correct all errors. And so we've demonstrated now not just a one-shot wonder, but we were the first to reach 3 nines. That's called 99.9% fidelity, 2-qubit gate fidelities on physical qubits. We've got the highest quantum volume across H1 and H2, 2 generations of machines. Very recently, we also demonstrated that you can write a much broader set of quantum programs than many others can. In fact, we are the only quantum computer that you can write what's called a universal gate set. What is the analogy to that? The analogy to that is if I gave you a processor today, Robert, and I said, by the way, my friend, you can do everything, but please don't do subtraction and addition. Right? Heaven forbid. If your algorithm requires that, you're kind of out of luck, right? If you're not universal, that is what a quantum computer does. You can only implement a certain kind of computation and not do the others, right? I can get into the specifics of it. It's called T gates and not, Clifford gates and non-Clifford gates, but it starts sounding like Clifford the cat after a while. But what we busted through, what the challenge was, is if you want to broaden the scope you're giving to developers by having all kinds of gates be or programs be written, you got to make them error-free. Right? You can't say, by the way, you can use all the instructions. If you use your multiplication, subtraction, 80% of the time is going to be wrong. That's not a value. So if you support it, you must support it with high fidelity. And that's what we were able to show. It's a fault-tolerant universal gate set on our machine, primarily because we have such high physical fidelities. And we can do error correction and detection so effectively.
That's fantastic, Raj. Now let's switch over a bit to impact. There's a lot of promise and some dangers associated with quantum computers. I know that the one that everyone dotes on is encryption, because now quantum computer can essentially unencrypt something, using Shor's algorithm, can unencrypt it relatively quickly or a lot faster than classical computing can. But there are other things that on a molecular basis, promise of quantum computing is rather significant. Can you touch on this? And also, are we at the point where we're able to do this now? Maybe you can give us examples. And when will we be at a point when we can do other things? So maybe in material science, energy, biotech. Yeah.
Very good. I noticed that I didn't answer your 100 logical qubit question, but you asked perfect question where the 100 logical qubit is a very relevant part of the answer. Right? So we'll get into that here. So, Jensen said, hey, it's 15 years away. Then thankfully he realized he was wrong, made GTC happen, which was great. And the industry got a chance to really show where we are, because that's what we as an industry should do. is put the cards down on the table. Where we are is we as a company are about 3 to 5 years ahead of where we thought we would be 2 years ago. So if you had me on the show 2 years ago and said, when do you get to 100 logical qubits? I would have said sometime at the beginning of next decade. Mm-hmm. We are building our machine called Soul, which we made public on our roadmap, with 100 logical qubits in 2027. So that's how much we've scaled some of these challenges in both hardware and software, de-risked some of the critical innovations needed by demonstrating them, and we are confident we get to 100 logical qubits. What does 100 logical qubits do? Right? It's not just 100 logical qubits, but the 100 reliable universal logical qubits. Yeah. Those open the door to real application benefits. I can give you 1,000 examples and you probably won't have time, but I'll leave one thought with you, where we are seeing a huge application and not 15 years away, not 20 years away. We are seeing it now in this business cycle because we are working with those companies on their use cases, is in things where AI is being used for, say, material discovery or some sort of intelligent search and decision process. And we are seeing quantum computers make that decision process much more effective, that is more accurate, and number two, much more efficient. Because if you think about it, today's AI, generative AI, is like a gigantic trial and error. It's a guided trial and error. In fact, someone from Google once described to me as a gigantic autocorrect, right? So it only knows what it knows, errors and all, but it only knows what it's been trained on. And the reason it's faster than you and I, and Rob, you can say, go use AI, Raj, is because the dang thing is so much faster than I am, right? So it can, like playing chess, right? I can do all the moves at the same time because it runs on computers. But what if it's not trained accurately? What if it doesn't understand the chemical pathways of a particular reaction and today makes a gross estimate of it and picks the wrong materials or doesn't come close to the optimized materials? Those are the examples where we are seeing quantum computers generate today the training data because it's accurate, it's chemically accurate. Remember, it's like how nature computes. So we get not an estimate, but we get actually things, what's called ground states of complex molecules. What is the lowest energy state of this molecule, right? Those kinds of things are no longer estimates and forecasts with classical techniques. They are actual measurements on a quantum system. Imagine how much more that LLM, that generative AI engine, is more capable of making now some of these decisions, like pick a molecule that we can then build to be a fire retardant, but it must have these following properties because it isn't parroting and mimicking what the world knew up until now. It actually has a tool to go do that experiment and say, okay, now I know I have real data to guide my discovery and help the human in the lab. So quantum computing, and I'm giving you just one example. It's being used in drug discovery, in new material formation, in pharma. By the way, life sciences and bio, as that is coming up. And basically things people had said before, we either don't have insight into how to represent these things, or we don't have enough compute power, even if we could represent them. Right. I've lived in HPC for 30 years. In HPC, it was either I don't have a closed form solution for this, or even if I did, man, it's going to take like 50,000 of the top, 50,000 supercomputers in the world working together to do this, right? So, but quantum computing busts through that. We now get to understand how chemical reactions work, how proteins interact with our body, right? And so these kinds of things, the human ability to be able to understand these phenomena, therefore be able to predict from it or even modify the phenomena, which is the creation of new materials, is fundamentally transformed and revolutionized by quantum computing. 100 logical qubits isn't magically the game end, but it is where folks like Microsoft, folks like us, folks like others who are working on real use cases start to see real value being generated. Like, for instance, you can now start to say, instead of starting with 30,000 molecules, I can only start with 30 because I have quantum computing to make me more accurate from that 30. I don't have to over provision the system.
Right. So it will potentially also help research and development and quicken that pace up dramatically.
That's right. What we are seeing is, and this is analysis in companies that are building new drugs. Remember, it takes about somewhere between 3 to 5 years to just do the discovery of the material, and then another 3 to 5 to 10, sometimes even 10, to do the longitudinal studies to show it's safe. Right? The patent lifetime is 20 years. So if you can cut down the time to market by 1, 2, or 3 years, that's billions of dollars for an individual drug of value created to the company. Right? How does the quantum computer do that? Well, it takes this trial and error and effective process of doing it today blindly into a much more informed and targeted way to search and create new materials. Also, we are seeing some of that data that is more what I would call accurate than estimations helps the downstream process and the regulatory phase. For instance, if we can say it's not just safe in these circumstances only after I prove it, after 3 years of testing, but it is the equations are showing, the fundamentals of chemistry are showing that it can never do X, Y, and Z, then you have a chance of actually even bringing down the regulatory time frame. Right? So it's those kinds of things that are transformative, right? We see quantum computing as fundamentally changing the way discovery and creation is done by humans. AI was a big step forward, right? Because you suddenly had this assistant with you that was infinitely faster looking at all options and it could make some decisions, right? And you just sent this AI engine that was high school level competence and had them get a PhD in every topic.
Yeah, and I would imagine that the amount of information that's going to be created is going to be exponential as well. So, all of this molecular information that normally would have taken years for a supercomputer to even try to calculate will now be
That's exactly
available and present.
We are seeing actual proof of those things, right? I mean, in fact, because it takes supercomputers so long to do even the fastest supercomputers, we can use that difference in time in things like encryption. We can say, how do you know this random number generated came from the seed came from a quantum computer versus someone spoofing you and giving you bits that they know? Is because there are tests that you can run and say, okay, if this comes back in 2 seconds, it must be a quantum computer because a supercomputer is going to take 2 hours to do this.
That's amazing, Raj. So one thing you mentioned was how quantum computing will integrate with AI. So there are challenges there. As you mentioned, you have to create a whole set of algorithms and, other types of programming for a quantum computer. There's been a lot of progress in terms of integrating quantum computing with classical computing.
Absolutely. In fact, we see the next decade or more being about hybrid. The use cases that's going to really bring value to society and companies and even in research is all a combination of classical with quantum. If you looked at our Japan project, the machine that we put in Japan next to one of the top 10 supercomputers in the world called Fugaku, the goal there is to build both the software plumbing as well as the applications that use both classical and quantum. We've been working with NVIDIA. We were the first company to actually work with NVIDIA to take our quantum stack and hardware and make it consistent under CUDA, what NVIDIA calls CUDA Quantum or CUDA Q, right? So people who are using classical computing and running AI, writing their programs with CUDA, could use extensions that could use our quantum computers, right, under the CUDA Q or CUDA Quantum. We just announced today our new software stack for the machine that we are going to release in a few months. And that software stack is primed, including a platform as a service element or a cloud front end, as we call it, to manage hybrid workflows. So that work, number one, the realization that the world's going to be hybrid between classical and quantum is now very well understood. And there's been a lot of progress in software, in standardizing interfaces, in making things compatible so that there are the number of ways you can use classical and quantum together on highest performing AI and highest performing quantum is tremendously more advanced than it was even 3 years ago.
And Raj, in terms of modalities and the kind of interface between various quantum computers, do you envision that some modalities will just win out over others, or do you think that there's going to be a way to integrate modalities? In other words, is there any possibility that you could have a multimodality quantum computer?
There's always a possibility, and if that happens by natural integration, so it still looks like one R&D effort, Robert.
Yeah. To your point, yeah, about it being
But
what's their
if
best
the world
fidelity.
gets into each kind of problem can only be solved by one modality, then we have an economic challenge because each of these must have the value created must be high enough to sustain the tremendous amount of R&D and capex that has to go into creating each of these modalities. We know we in one of those we spent $1.7 billion over the last 10 years being the leader that we are today. This is not cheap. We actually believe, I wouldn't say that the trapped ion R approach is going to cover 100% of the use case space in the best possible way. I'm not going to say that. But our goal is to build the best general purpose quantum computer that covers the broadest set of use cases in the highest performing way. Because we think that is A, possible, B, it's necessary for the economics of the industry. And 3, it is the way to get the industry to move faster. Walled gardens have never moved as quickly as standardization, as open APIs, and that's what our commitment to open source is.
Raj, thank you for this session. It's been very informative to me, very insightful, and I know I can speak for our listeners that this has been very informative. I really appreciate it. I could talk about this for hours, but I imagine you'll want to get back to your family at some point.
Thanks for thank you for having me. This is a huge, sometimes I tell my kids this. You only know how big a moment was once the moment has passed and you're enjoying the benefits of it. 2025, which is the International Year of Quantum, is like that. Yeah. I think while many of us in the throes of it are realizing what the industry is doing, what the world is seeing, and what society is going to have access to, I think it'll fully only dawn on us a few years from now. Yeah. And we'll have the first quantum AI generated drug, when we have the first, of these things that couldn't have been done before. That's when we'll say, but it all started with.
Yeah. Raj, thanks again. Thanks so much for being with us. This podcast was recorded on August 20th, 2025. Join us next time when Anne Malone and Jeff Meacham will discuss biotech.
This podcast contains thematic content and is not intended to be investment research, nor does it constitute financial, economic, legal, tax, or accounting advice. This podcast is provided for information purposes only and does not constitute an offer or solicitation to purchase or sell any financial instruments. The contents of this podcast are not based on your individual circumstances and should not be relied upon as an assessment of suitability for you of a particular product, security, or transaction. The information in this podcast is based on generally available information, and although obtained from sources believed by Citi to be reliable, its accuracy and completeness are not guaranteed. Past performance is not a guarantee or indication of future results. Third-party opinions expressed in this podcast are solely those of the speaker and do not represent the views of Citi. This podcast may not be copied or distributed, in whole or in part, without the express written consent of Citi. Copyrights 2025 Citigroup Global Markets, Inc. Member SIPC. All rights reserved. Citi and Citi and Arc Design are trademarks and service marks of Citigroup Inc. or its affiliates and are used and registered throughout the world.